Now that we know a little bit about linear approximation, let's use what we know to discover differentials. We've learned that the value of our function at x will be very, very close to the linear approximation at x. So f of x will be approximately L of x. And because the equation of our linear approximation takes the form m times the difference of x minus x sub 1 plus y sub 1, we know that our actual function f is going to be approximate to m times the difference x minus x sub 1 plus y sub 1. But let's subtract the y sub 1 from both sides. That gives us f of x minus y sub 1 is approximately m times the difference x minus x sub 1. So what's the hidden meaning behind this simple expression? On the left, we have f of x minus y sub 1. Well, f of x is just the value of the function at a certain x. So really, that's just a y value. So on the left side of this expression, we have y minus y sub 1. That y minus y sub 1 is just the change in height of the function. It's one height minus another height, which is a change in height. And we're going to call that actual change in height of the actual function itself delta y, which just means change in height or change in the y's. Now let's look at the right side. The variable m is just the slope of our tangent line at a given x value. So that m can be represented by f prime of x because it's simply the slope of the tangent line at a given x value. And then what about the expression x minus x sub 1? Well, that's just a change in x values from one x value to another. So x minus x sub 1 is just the change in the x values. And we're going to call that delta x. So what does all this mean? This is so powerful. This means that delta y, which is really just a small change in the y variable, is approximately equal to the corresponding small change in x, and the only thing that differentiates these two small changes in y and x is a factor of the derivative itself. This shows us that a change in y can be approximated by the corresponding change in x, but that change in x is going to be magnified, overestimated, or diminished, underestimated by a factor of whatever the value of the derivative is at that certain value for x. Okay, so what does all that mean? What did we just show? We just showed that the change in the actual value of a function as x changes incrementally, we're going to call that change in the value of a function delta y. So delta y is the actual change in height of a function as x changes little by little. And we just showed that delta y is approximately f prime of x delta x. Now we're going to define the change in the linear approximation as x changes incrementally. And we're going to define that to be called the differential. The differential dy. dy is the differential. So dy is equal to f prime of x dx. So the only difference between these two expressions is this one monitors the actual change of the function itself, and this one monitors the change of the tangent line. And we know that the value of these two expressions for a given value of x are going to be very, very, very close to one another because they're almost indistinguishable from one another. This means that if a change in x is incrementally small, then the corresponding change in the function value, the actual function itself, delta y, will be very well approximated by the change in the linear approximation dy. And the approximation of delta y as compared to dy will improve as the change in x gets smaller and smaller and approaches 0. That means the closer we are to our point of tangency, that means that the delta y is going to get very, very close to the dy, and the dy is going to get very, very close to the delta y. So the closer we are to our point of tangency, the more our graph actually mimics the graph of the tangent line. So we have delta y, which is the actual change in the height of the function, will be very, very close to dy. And we know that dy is equal to f prime of x dx. That means that delta y is going to be very, very close to f prime of x dx. And if we look a little bit deeper, we can see that the notation for differentials is consistent with the notation for the derivative. We know that dy is equal to f prime of x dx. But if we divide both sides of this equation by the differential dx, we get dy over dx equals f prime of x. And that makes complete sense because the notation we've been using for the derivative is dy over dx. And that does equal f prime of x.